Can you see the screen, the class note?
Yes, sir.
Well, this is the continuation of the last class. It's a dynamic logic. Last class is a production. This is the same diagram. So yesterday we have seen that there are some problems with those dynamic logic. So one of the problem was we mentioned here that for this circuit, the same circuit as yesterday, same circuit as yesterday, and you see when we have let's say the third input condition. No, not third. Actually, this one is fifth input condition. Okay, let's say A is equal to 1, B equal to 0, and C equal to 0. And the clock, of course, clock is 1. In this time, the output is 1, and Y bar will be 1 because the capacitor is fully charged. But the transistor A, you see the input A is 1, so that means the transistor A is on. So in this case, this, yeah, I also mentioned yesterday the capacitor, the charge from the capacitor, this load charge from this load capacitor will be discharged through this A transistor, and this capacitor CA will be charged. So then the load capacitance charge will be decreased, and the voltage and the output will not be same as VDD. It will be degraded. Right? And if we do this kind of operation several times, let's say now in this case, the load capacitance, the voltage at this load capacitance is decreased a little bit, and because of the charging of CAB. And the next time when we turn off A and turn on B, let's say the A is 0 and B 1 and C 0. What is that condition? Is A0 B1, let's say the third condition, A0 B1 and C0. In this case, let's say the A and C transistor is off, but the B transistor is on. So the charge from the CAB will be discharged to the ground because the foot, you see the footer transistor is always on. So that means the CAB, whatever the charge was in CAB, will be discharged through the B transistor and will be 0 at that time. And the next time again, if we go back to the previous condition, let's say A is equal to 1, this condition is A equal to 1, B equal to 0, and C equal to 0. A equal to 1 and B and C are 0, so that means B, C again off, but A is again on. In this case, the voltage of the C load again will be discharged through the A and will charge the CAB. So that means the previous time, for example, initially the voltage at the load capacitance was full voltage like VDD, let's say 1.2 volt, and the first time when it discharges and charges CAB, the voltage drops. Let's say the voltage dropped to 1, from 1.2 to drop to 1 volt. And now again, if we do the same condition, same inputs, then this voltage, output voltage 1 will be reduced to further down to, let's say, 0.18, 0.08. So if we continue this kind of operation, then after several times, the voltage at the output will be less than 0.5 or less than the threshold voltage. And if it goes less than the threshold voltage, then this output will not be considered as logic 1 anymore. It will be turned into logic 0. So that is a dangerous condition. So how can we fix this? So in order to fix this, this is what I have said, These are written here, so you can read it. And this is the diagram, the modified diagram. Here you see the output is connected to an inverter, and the output of the inverter is connected to the gate of a PMOS here, and this PMOS is actually parallel to the original PMOS. In here, this is original PMOS, and now this PMOS is connected in parallel and is connected. You see the upper side source is connected to VDD. So, and this will solve that problems. How does it solve? Let's say here, we'll go like the same condition. Let's say the A is 1 and B and C transistor is 0. So that means A transistor is on and B and C transistor is off. So the load capacitance will be discharged. So the load capacitance, let's say C load, the load capacitance will be discharged through this path and will charge the capacitor CAB. But in this case, you see, when it will be discharging, at the same time, this output is 1. The output is 1, that means this inverter output is 0. And when the inverter output is 0 means this PMOS is known as keeper transistor. So the keeper transistor is on. So when the keeper transistor is on means short circuited. So the power from VDD will be passing through this keeper and will charge this output capacitor at the same voltage as VDD. You understand? So this capacitor is discharging, so its voltage is reducing a little amount, but at the same time, the voltage from VDD will be coming here and will discharge again at the full voltage. So this load voltage will remain same at all time. Even it is discharging a little amount to charge the capacitor between A and B, this is a capacitor, but the charge will coming from VDD and will recharge and will remain the output voltage strong 1. Do you understand the problem, how to solve it? Any question? And by using an extra keeper transistor and an extra inverter, so we can solve this problem, as we mentioned before. Any questions so far? Anybody? Hello? No, you understand well, okay? Right?
Yes, sir.
Yeah, I have already written here. An extra PMOS transistor is added in parallel with a former PMOS. This PMOS is known as keeper transistors. The gate of the keeper transistor is connected to the output through an inverter. So in this configuration, if the load capacitor is lost some of its charge, then it will be fully charged through the keeper transistors, because the gate voltage of the keeper is 0 logic as the output is 1 logic. Right? The output is 1, so it will be 1, and then here will be 0, and this will be on and will be discharged. Right? So this is the technique. But you see, and in this case, so we need an extra transistor in here, keeper transistor, and also we need a 2 transistor for inverter. Right? So we need an extra 3 transistors. But in this small circuit, it is not savings, but for bigger circuit, we need only 3 extra transistors. On top of those, so many transistor PMOS is here. Right? Let's say if we consider 50 inputs Boolean equation. So instead of 50 PMOS, we need only 1, 2 PMOS, and in here another PMOS, 3 PMOS, and 1 NMOS. Instead of 50 PMOS, we need 3 PMOS, 1 NMOS, and also 1 NMOS in the footer here in the bottom. So we needed 2 NMOS and 3 PMOS instead of 50 PMOS. And so we can save a lot of transistors here. So that's a good thing. So it will save the space, and also it will save the amount of power required to run those transistors. Now see the other one. Last class we have seen the layout diagram. We have seen last class, and okay, if you look at those diagram here, normally if we consider the standard diagram, let's say to look at the bottom one. This is the original diagram for the original CMOS original circuits. Right? This is a B, C, only 3 inputs, and will be connected like this. Right? So it's one VDD and one BSS here. So this is the diagram, right? And we can make it layout from there. So now look at the area. How much is the area? Area will be this much, right? So this is from here to here will be the maybe the x-axis, and y-axis will be here to here. Right? This is not the right one, right? This is a mixed mistake. It will be go up to this point. So this will be rectangular area, right? And now if we use this same style and design the CMOS stick diagram for this circuits, right? This dynamic logic circuit, and you see here there is a not this one actually. This is the original one. In here, this is a 1 PMOS and 1 NMOS are connected as a clock, and 3 NMOS is here. So now look at here. How do you design this? Here you see this is a clock. This red one. This is a PMOS and this is NMOS. And the extra 3 NMOS is here, A, B, and C. Right? And we need to connect like this. This is a source of the NMOS will be connected to the VSS. No, this is a clock. Source of the clock NMOS will be connected to VSS, and the drain will be connected to the junction point of B and C here. So it's connecting here. Both are source. So the other side is drain. This side drain and this side drain. The drain of the B will be connected to the source of A, and the drain of the A will be connected to the drain of the C and will go to the output. Right? So now look at here. In this diagram, we have a 1, 2, 3, 4 NMOS in the bottom side. Right? You see the bottom side is 4 NMOS, but in the top side we have only 1 PMOS. Right? And you see the rest of the area. In this area there is nothing. Have you seen that? So this area is blank space. But the area should be calculated as a rectangular area. Right? So we have to calculate the rectangle. Right? So that means we have to take all this area. Right? From here to here, you see the red marks. So we need all this area, though there is no more transistor here in the blank space, but still we need to use that area. So that area will remain blank. Right? But we need to use that silicon though. Right? So actually we cannot save the space. You see, in this diagram, this area remain blank in the integrated circuits, though there is no transistor there. So that means we cannot save the area of a silicon. Right? We cannot save. That's why what we need to do, we need to arrange this A, B, C transistors in a vertical way, Right? Instead of this x-axis, we have to put it in y-axis, just like yesterday we did in the y-axis, and then we can save. And look at those diagram yesterday. It was a little amount of area here, like this kind of rectangle. Here I am showing by mouse. Right? This was like this much, and now but if you use this kind of diagram, lots of space will remain blank in the integrated circuits. Understand? So that's why we should not use this kind of diagram, and the layout will be designed according to the rule, according to the style I mentioned yesterday. Right? It's in a 90-degree rotation. Right? So I think okay, so that will save the area. Other, if you use this kind of diagram, then this time in this case the area will be more than the original diagram. You see this original diagram, we have only A, B, C, 3 transistors, but in this case, this amount of area is up to this point, and dynamic logic diagram is this whole area. So whole area is bigger than the original CMOS logic diagram. So, so that's why we do not use this kind of this style, right? So, any questions so far? Do you have any question? Can you hear me? Hello? Can you hear me?
Yes, sir. We can hear you.
No question. So we have only 11. So I don't know why so few. So we have to end the class today because of the very short, very few number of students, right? And we'll start tomorrow at the same time. Right? We'll start at 10 o'clock tomorrow again, and we'll discuss another topics. So please, yeah, ask your friends and to ask them to join. And however, I am going to post this lecture soon. Okay.
Yes, sir.
If we don't have any question, then I will need to terminate. But I have another class at 11 o'clock. Okay.
Yes, sir.
Okay. Bye then. Have a great day. Bye.
Thank you, sir. Shalom, sir.